Okay, so thank you, Sven, and also thanks Nick and Tisha and all the others, for friend and others to invite me and give me this opportunity to talk. And I kind of feel very deeply gratitude to all the things um, I have in my career. So here is the back. So we saw a lot of LA this photos with Jack's car. But I also must point out we had a lot of fun. We had once a few months during that development, we will have a get together and have a very intensive discussion. But nevertheless, we also do a lot of excursions and spend a lot of times hiking. And this is a group of photo. It's in the Smoky Mountains. So when we at Tennessee, as you can see, we had Jack and also Sven, Jim, and also Jeremy, and has a lot of profound impact with us. Unfortunately, cannot join us today. So, but personal levels. So this is really two things struck me at a very it's just some minus, but nevertheless has huge impact even up to today. So my career started as first visiting exchange students to University of Maryland. I was work with Pete Stewart. And then after spending a little over a year with Pete, and then Jim Demo recruited me and to working on the LA pack. So I fully plan and also sort of go back to China in 1989. So after 3 years stays in US, and then to get my, a job and establish my families and so on. So, but of course, we all know what happened in 1989. So I really feels lost it. But then Jack rescued me and offered me a job, and with him to Tennessee. So I was one of the very earliest employee, might call it on Jack's the ICL, and now called ICL. But back then, Jack just moved to Tennessee. He and Ed Anderson and I shared, basically they converted one of classroom to Jack's office. And then we're using this binary divider between the Jack's office and also Ed and my desk. So of course, once Jack gone, I've used Jack's desk, much bigger than my little desk. But I feel really personal level, feel really lost it, what to do, what's the next step, etc. So that's the end of 1989. And then one of the morning, I believe Jack find this cartoon from his newspaper read, and then he cut it off and bring it to office to me. It's really struck me. It says that, I have some specialty. I should do something in my career and not thinking about it, of what's my plan. I just should focusing on my of that. And this is a particular, if you're looking at the caption on that, it's my specialty is linear algebra. May heaven help me to do something. So this cartoon, I even keep that up to today, still in my folder of that. The second of that is very iconic is recipe. This is Sue. So after I left Tennessee and got the job at the University of Kentucky and started married 2 years later with Wendy. So we are still, none of us knows how to cook or how to do something because of that. So we still visit Jack and from time to time. And then one of course, as you can see, this is a potato casserole, and this is a Sue, the handwriting. So we had a dinner at Jack's house, and we very love this dishes of that. We're so amazed. So Sue is so patient, write down the whole recipe for us. We still have this card. Wendy using it now. Every holiday, every Christmas Eve, we make this potato casserole based on this recipe. And also as the other, if you probably cannot see this corner of that. So we had a lot of wonderful parties at Jack's house, and assume every ICL employee can testimony that. So as you see, this is a very big recipe prepared for 12 people. So within all that, I really, with deep gratitude, want to thank Jack and thanks Sue, not only professionally, impact of all the research I have been doing in the last 30 years so, and also for my families, etc. Okay, within that, so now I'm going to talk about of this very classical problems. I picked this one. I feel it's illustrating both of the topics of this workshop to celebrate Jack's birthday is on numerical linear algebra and higher performance computing. So the problems we're talking about here is it's basically say you're giving us a metric or Hermitian matrix. So you want to quite many of the eigenvalues and eigenvectors. So you talk about the matrix size, if you comparatively is called huge, and the number of the eigenvectors, the eigenvalues you wanted is pretty large. And of course, we see the increasing demand for such a request. Even in fact, just a few days ago, a group of people at the LBL and asked me about these issues, etc., how to do. So of course, we all know there's plenty of the tools we can use. So first is you can just consider to using a full eigen decomposition. So this is, as you can see, this is the first few like LA pack, scalar pack, and megama, plasma, etc. And also very specialized in the big solvers from Japan and other group. And more recently, and David and his collaborator at KAUST, and also Tennessee group has a lot of development continue. But nevertheless, it's very stable, but nevertheless, the cost is the primary concern. The second is more from the iterative methods point of view. So you can think about it, if you want a lot of eigenvalues and eigenvectors, so you can consider cut them into a different slices, or use called windows, and you can compute one patch at a time or compute multiple of such slices simultaneously. So this is under all those packages from SLAP-C to Z pairs from Japan's group, and or more recently, this shifting, inverting the slicing and Chaoyang at LBL developing. So nevertheless, all those methods is aimed at scalability at high performance computing, but nevertheless, there's quite a different issues within the duplicating and missing the eigenvalues between all those slices, windows, etc. So many of those methods and based on the iterative method I'm focusing on. So is based on some sort of subspace projections. So of course, we all know that here is the primary is one issue is if you want many of the eigenpairs, typically you need a large projection subspace, which means a big memory footprint. And the next is that you need to avoid because for different eigenvalues, the convergence rate may be different, but you need to have some mechanism to locking or deflating to those computed eigenvalues to avoiding the dangers of computing them again. So those are so for doing both of this, so you need a big memory and also to do deflations, so you need quite a bit flops. And of course, those flops operation, it's not like a typically of a blast type of things. So there's a lot of effort try to how to do this more efficiently. For example, yesterday, and Fran talked about this tall skinny QRs. So this is quite required in such kernels for internal deflation. So, but nevertheless, even up to today, we still have a lot of quite a bit challenging. So this is slides I already using quite a few times to make the cases. So in this structural biologists, they studied this molecule or this virus, how it's evolved. So there's a popular database to collecting of different types of the virus. So if you want to computing this matrix size is roughly 300,000. So they need roughly about 5,000 of eigenpairs. So you can partition those eigenpairs into different slices. This is a very popular recent package called the EVSL, is spectrum slicing techniques. So you can computing them, and this is this photo to show the computed eigenpairs, this 5,000 eigenpairs, the residuals, etc. And this is the red of this on the right-hand side is talk about this using a polynomial filtering. As you can see for the exterior eigenpairs, so the degree of polynomial filtering is quite low. But if you move towards the interior of the spectrum, the degree of polynomial filtering getting higher and higher. So this reached to 300 plus. And also the CPU times to computing those eigenvalues moved into an interior, also getting higher and higher. As you can see, it's quite a substantial increasing of that. So it's really called for more efficient, you might call it, of primarily is memory issues. So this is exactly the talk associated with communications, and Jim demo mentioned yesterday. So therefore, right now, so this talk, I'm going to, for the remaining about 10, 15 minutes, I'm going to talk about this. We are working on this nla-group type of eigensolver, whatever that, but using a more classical deflation techniques called Hotelling deflation. And then, of course, for the higher performance is about this, how to do that in a communication. So this is that. So within that, so this is of that, I will talk about this, the rest is within those parts. But of course, probably I don't get the time to talk about all the detail, but I try to at least quickly go through what they are. So this is a joint work with Jack. In fact, so I talked to Jay with Jack. So because of when his Ichitaro Yamazaki working with him, and Jack generously supported and worked with us, and also currently with my current students, he's graduating and going to work for this. Actually, the very similar problem for Siemens. He's got a job there. And also this Dingru, so this is a joint work with them. So let's start it. So what is called a Hotelling deflation, or I give a more specific names called explicitly external deflation. So it's a very classical algorithm, or you might say idea. So here it's slightly in terms of modern terminology instead of the original one as presented in the Wilkinson's book. So basically, let's assume you have a standard eigen decompositions, and then you have a bunch of the eigenvalues, eigenvector, which here is called Vk, and the lambda k is already computed. Then you can define a new matrix, it's called A hat, which is essentially just original matrix and a plus of that within the updates of those. Then you can easily show for this A hat matrix, it's all the eigenvalue within the lambda k is being shifted by this sigma I, whatever shifter you use. And then for the rest of this, it's unchanged. So therefore, essentially within this, you can declare this, say that for those I already computed, I can move them away, and then using this eigensolvers, whatever eigensolver you are using to compute the next batch of the eigenvalues and eigenvectors. So this is a very classical, and probably you will learn once after you learn the powers method, and then the next say, what if I want multiple of that? Of course, one is you go to blocking, or the other is you go into such deflation. This is exactly presented in the Wilkinson's book as it is. So if you put it down this as a sequence of deflation, this you might call the governing equation for that. So we will come back to that later. So why we are or why from my personal angle of my group in terms of working on this particularly interesting such techniques is that first, of course, we find it's very easy to incorporate whatever the eigensolver, or you think about Siegfried-Style Lanczos, ARPAC, or whatever you are favored, because in this case, all you need to do is that for whatever your eigensolver, once you computed a patch, essentially your eigensolver just need to apply those A hat. In other words, you just change the matrix vector multiplication of that. It's very simple. It's completely external, nothing you need to touch inside of that, of your code. And also in this case, so now because each time you call eigensolvers, you only need a very relatively small number, even you want to have 5,000 eigenpairs, but you can only do 200 at a time. So in this case, your internal memory requirement, or we call it core memory, will be very small. That's of that. And also the second is the other concern is that typically this is because you have a small memory, all those eigenvector you already computed. So if you still keep them internally, so you need to orthogonalizing or re-orthogonalizing to those explicitly. If any of us had working experience within this, we know this is quite expensive process and also very tedious to do that properly. Just looking at quite a few papers written that follow the ARPAC development. So the other is, in fact, if you're only computing of a patch, and then you have some additional the vector, which is nearly converging, but not quite convergent yet. So you can reusing those as we call a warm start for the next phase of differentiation. So you will find that it's going to be pay off very easily. But of course, the rest is more talking about how to extend it to generalized eigenvalues, eigenvector problem. It's non-trivial if you do that internally doing differentiation. And also we have quite a few structured eigenvalue problems. One of them I have been working extensively on for a few years on the linear response eigenvalue problems. And of course, today people also interested in the sparse PCA, SVD, etc. So all this type of techniques, if you use the multiple ones, you need a multiple ones or many of them, you can using such a explicitly external differentiation or Hotelling type of differentiation quite easily. I think this slide is really show why we are advocates to such a very classical techniques on that. So, of course, for such technique to be a viable techniques, you need to have two critical issues immediately come up. More is I call it numerical linear algebra issues. Basically, how stable of such method is. Essentially, because you are not using the exactly eigenvector to do the differentiation, inevitably you might call that those errors are going to accumulating. So essentially, how reliable over in the end. Okay, so of course, secondly is that the matrix you threw away the you might say computed one outside of this your memory kernel now, core memory now. But nevertheless, when you do the matrix vector multiply, you have to deal with this big matrix A and plus this lower rank. You might call it relatively lower rank, but nevertheless, it's generally it's dense. So therefore, how you can do this matrix vector multiply, and this is really fast or efficiently. This is more, I call it higher performance computing issues. So essentially for the rest, I'm going to addressing those two issues. And to particular, first one is rather recently, we completely finishing a numerical analysis, or you might call it backward stability analysis. And so for second one, high performance computing issues, I have already, or we already have talked about it in IPDPS conference a couple of years ago, but we also have some recently collected some new data. So regarding this Hotelling deflation, if you're looking back at the literature, starting from Wilkinson's book until some recently study, the signal it has a very, I call it a mixed message, meaning that, for example, Wilkinson basically say, because the shifter is using the exactly computed eigenvalues. Okay, so that he basically say the numerical could be quite unstable. So I do not recommend it to use it. But when you're looking at Paley's book in chapter 5 of his book, so he talk about this, he basically indicating is that if you're going to compute deflating those of that, the impact to the larger one, meaning far away from those deflated ones, are in fact is much less impacted. It's very, it's essentially to machine positioning, there's no impact. So in other words, it's quite a conflicting message from those two, not a conflicting, meaning that different perspective, from those two classical study. Of course, before we had an implicit restart within Danny Sorensen's work, we also have Yusuf Saad did a quite intensively study on those explicitly diffusion extending to et cetera, et cetera. So today, essentially, what we do is that we back to the drawing board and started within this, we start classically governing equation. Then we in exactly the case, so we will have this so-called of this order error terms will be involved in terms of in the analysis. So then within this of a set of the equations, so we talk about it. If you say your algorithm is stable using this, we really want meaning that is the all the computed eigenvalues, eigenvectors within the residuals, the orthogonality will be under the tolerance, the value you set. And also if you're looking at the backward error norms and defining these classical terms, it should be at the machine position times of norm. So this is our criteria of the backward stability. So in other words, now within of a quite extensive analysis, very carefully goes through the floating point error analysis. This is Nick Hines, basically using all the standard formula in Nick Hines' book. You go to the step-by-step analysis. And then within we introducing this two quantity, and one is called a spectrum gap, basically say how far you move your computed ones. And it's not the far the better, okay? So, but nevertheless, this quantity, how far you're away, meaning associated within this shift, are the one of the quantity of essential quantity. The second is that I talk about it, you cannot move too far away, meaning the shift you pick cannot be too large. So therefore, there's a proper ratio between the shift and the gap of that. So then afterwards, this is the after field theory, lemmas, etc. You can rigorously prove if you are the spectrum gap and within the ratio within the norm of matrices, which is basically the spectrum radius, you might call it a span. And if you have properly the order, both at the constants order, you can rigorously prove this the loss of orthogonality and also the backward error norms under this. So therefore, within this results, to really narrow down how you can, in practice, or we call the rule of thumb, how you can properly select in such shift to maintenance the backward stability. So this is basically of the, we test a bunch of the matrices. I think that we don't have times now. So essentially, as you can see, for all those different set of matrices, computing relatively to the matrix size, large number of that, we do multiple deflation. As you can see, the primary is the fourth column and fifth columns here for all those different type of matrices, and we can maintain all the computed eigenvectors and eigenvalues under the backward error sense. And also the other one, we have not missing any of those eigenvalues within, we use alternatively using the other way, using through the initial to know how many eigenvalues in these intervals, etc. So we find that we have uniformly calculating all this. So the other is that you might wonder if you do even, this is sequential sense. So even with because of matrix vector, we've not talked about parallel yet, okay? So matrix vector will be, cost will be increasing associated with deflation, but because of internal memory usage is low, it's turned out that this last two columns to show you this, if you use the Siegfried Lanczos TRLAN, and you are computing the eigenvalues using this deflation or without using this exploratory deflation, we are not increasing the times at all. In fact, we are also slightly improve the performance even in regular sequential cases. So this is our work as just put on the archive last month. So if you're interested, you can looking at the details of that papers. So I think I'm running out of time. I think some of you already have seen, because I've been talking about this matrix vector multiply. Basically, you have sparse plus low rank matrix. So you want to keep doing the matrix vector multiply, forming this Krylov subspace type of method. And so one is the standard way of you doing that is just using this matrix loop. So this is simplest loop you can code up to do the performance. But nevertheless, so this is in MATLAB for students, this is particular I advocate to the students of that. If you code up this, you will see this is the speeding. If you're computing about 20 of such vectors, so increasing the timing was just you might call it linearly increasing within that. But nevertheless, there is a so-called communication avoiding method. Instead of you bring the references to this kernel of vectors multiple times, then now you can do that in a much only doing reformulated these formulations, and you can only upload or accessing such vectors twice, and then you are for the rest of computation you are accessing much smaller number of the vector you calculated. So your performance curve is just this red curve. So this is basically a very striking of that. So we have data on the different platforms and to illustrating this basic kernel. In other words, this matrix vector multiplies, you can explore the of this low rank structure or properties, and then you can reduce the communication of that. Of course, this part of the work is really relied on the very early work, not very early, just a few years back, and Jim and his students, Nick and Erin Kaufman, and looking into such a structure. So we are basically fully implementing this and looking at the different type of structure of that.
Thank you.
So, yeah. Okay, so I'm finishing up. So basically, this is a lot of you can experimental then on MATLAB, and of course you can also do that on. This is a set of the data we collecting on the NERSC, the supercomputer and the Cori, and then finally, if you put all the eigenpair together into the this deflation plus the matrix power kernels. And then within this variance of this so-called of Secret style doing the S-step fashions. So you really get the speed up of on the multiprocessor of speed up as you can see if you have a multiprocessors of that. And the one is the blue curve, just the standard of a TRLAM with some blast level of parallelism. But nevertheless, if you're using this red curve to show you the speed up almost linearly when you do computing within that. So within this, so I say first, this so-called mini eigenpairs probably, if once you build it, they will come. That's the one of the another messages because it's increasingly demanding. But my talk is more on this specifically of these two techniques on that. Also, the second one, I think I went way too fast. So within this, so that's all I want to say. Oh, also, over the weekend, July 4th was Bear's 4th birthday. So I sent a greeting to him and tell him I'm attending the Jack's of that. So Bear's 4th Tale sent his best regards. And also he said to him, 70 is so young. So because the Beresford College just had his 89th birthday. So he's sharp. If you send him the emails, he responds in a few minutes if in a time frame. So Jack Beresford send his regards to you.
Oh, very good. Thanks,
yeah, thank you.
Thank you very much. Bye.